Critical thinking question number 1, and how CO2 and global warming work with CO2 and ocean acidification. Now the question is asking, in terms of global warming, why might ocean acidification be a good thing? If CO2 is in the air, it leads to global warming. So why is ocean acidification maybe a good thing? Well, because CO2 will enter into the ocean. Okay, so this is if this happens. So this equals less CO2 in the air, which is equal to less global warming. So again, in terms of global warming, why might this be good? Well, if, again, CO2 is being absorbed into the ocean, there's less CO2 in the air, which will lead to less global warming. Now what scientists didn't know is that this will increase ocean acidification. So that's the one piece they didn't know. For a long time they thought it was a good thing because it was helping out with global warming, without realizing that it was contributing to ocean acidification. Alright, critical thinking question number 2 is talking about adding iron into the ocean. If iron is added into the ocean, it equals or leads to more plant-like organisms. Now these plant-like organisms are going to intake or take out CO2 from the water. But why might this be a bad thing for the shellfish industry in the short term, but good in the long term? Well, these actually make shellfish not edible. Okay, so you can't eat it. So this equals to a loss of money. Why? Because the industry can't shell poisonous shellfish. Okay, so they can't sell these things. But why might this be a good thing? So why might this be okay? Remember, if it's taking CO2, this will lead less CO2 will lead to less ocean acidification. Now if you have less ocean acidification, this will equal saving shellfish in the future. What happens if you don't do this? So if you don't add iron, so if you just have water and you have CO2 coming in, okay, no plant-like organisms, so these guys are not in there, this will increase ocean acidification. This will lead to shells dissolving, which will lead to no shellfish, which will lead to no money. And shellfish dissolving has to do with those hydrogen ions that we talked about. So here's the two things to consider. If you add in iron into the ocean, it will create more plant-like organisms. This is going to make shellfish not edible in the short term, so businesses will lose money. But in the long term, you will save shellfish because there's going to be less ocean acidification. If you don't do this, CO2 will enter in, ocean acidification will go up. Can you still sell shellfish? Yes, but over the long haul, shells will begin to dissolve or at least become smaller. Less shellfish, less money. Alright, critical thinking question number 3, how did we contribute to ocean acidification in the lab? When we put yeast in with sugar, it began to produce CO2. That's the little bubbles that were popping out, and we're measuring the change in water. So, because of the lab, we actually produced more CO2 into the atmosphere. CO2 in air will eventually mean CO2 in water, or seawater, which will turn into H2CO3, which will split into your HCO3 and your H+. This H+ will lead to a lower pH, which means higher acidity. So by us releasing carbon dioxide into the air, eventually that's going to make it into water. It's going to turn into carbonic acid. It's going to split, create a loose hydrogen ion, which will lower the pH of the ocean, increase the acidity. So inadvertently, because of the lab that we did, we added in extra carbon dioxide into the atmosphere, and it will eventually lead somewhere down the line to an increase in pH because of these loose hydrogen ions. If not, even if it doesn't increase pH, this loose hydrogen ion is going to attach to a CO3 minus, so these two are going to combine to create HCO3, which cannot be used. This is unusable to shellfish. So that's how we contributed to ocean acidification by producing CO2 in the lab. Okay, critical thinking question number 4. This is the comparison of pure water to salt water. Now, in both cases, you have H2O, and we know already that when you add carbon dioxide into any of them, it's going to form carbonic acid, H2CO3. The H2CO3 is going to split into bicarbonate and a loose hydrogen ion. Now, the thing you have to understand is pH, okay, is controlled by the hydrogen ion. pH is a measure of hydrogen ion. If hydrogen ions go up, pH goes down. If hydrogen ions go down, then pH goes up and becomes more basic. So again, it's the hydrogen ion that the pH meter is measuring. So when this happens, if you add in one CO2, pops off a hydrogen, your pH goes down. Okay, it gets more acidic. If another CO2 comes in, pops out another hydrogen, your pH goes down. Another CO2, pops out another hydrogen, pH goes down. If you notice, as carbon dioxide is coming into pure water, only H2O, you're just popping out hydrogens. What about salt water? So again, your pH is going to start dropping because you're pumping out a lot of hydrogen ions. Here, CO2 comes in, turns into carbonic acid, splits. But you got to remember, what else is in seawater? You have calcium, and you have your carbonate. Now, when this splits off, when this hydrogen splits off, it's going to want to combine with your HCO3 and turn into, your H plus is going to want to combine with your CO3 that's floating around and become bicarbonate, CO3 minus. Now, if we go back to this, pH measures loose hydrogen. When this attaches to this, it's no longer loose hydrogen. This hydrogen is basically invisible to the pH meter. So, in pure water, you have hydrogens being pumped out. It's not sticking to anything. It doesn't attach to anything else. This is just pure water. Here, in seawater, a hydrogen can pop off. It takes away the carbonate, which is the bad thing in ocean acidification. If it's taking all this away, there's less shellfish or less shell formation. And you get this. You don't get the loose hydrogen. So, again, in this case, seawater, okay, will go down more slowly than pure water. Again, it's pumping out pure hydrogen, and in this one you are not. You're creating bicarbonate and slowing down the production of loose hydrogen ions.